So today I'm going to talk about real statistics, components of statistics. Until now, we were kind of thinking about how to apply statistics, the meaning of each one when it's applied. But now we're going to talk about real statistics. But before I go on, by lecture number 4, you will have to come up with some research ideas. And by research, the lecture number 5, you need to crystallize your ideas and then present with what you want to do, what will be the primary hypothesis and outcomes, and yeah, we'll do that. Each one of you will go around and talk about it.
Lecture number 4 would be next time.
Mm-hmm.
Okay. So in a week we have to have our whole research idea?
Is lecture number 4 next week?
Oh, sure.
This is lecture number 3.
This is 3.
So
When is
next week
lecture number 4 will be provided by Dr. Sang, Chi-Hong Sang. And lecture number 5, also Dr. Sang, but by the time you are ready to discuss, I'm going to join.
So for next week, basically, you want us to have a research question, hypothesis, and what else?
Hypothesis, outcome, you can just come up with maybe several ideas. If you do, maybe if only have one, then that's fine. But we'll be able to tell you. But we'll give you some little like guidance.
You don't need a study design, do you?
We'll come up with that together.
Okay.
As we discuss together. And by 5th lecture, you will crystallize and then we'll still be modifying the study designs, I think. Study design is not that easy sometimes, but we encourage you to come up with a simple study design.
Just a question, for pilot studies, do we need power test or not?
So for pilot studies, there are studies that you do it for the very first time, nobody had done before.
Yes.
Then you have no idea what you have absolutely no idea what the outcome estimate would be. Then, but still, some statisticians want to see, okay, do you have can you provide any number that will give you some kind of, because you have to plan your study, right? Then in that case, we normally suggest like come up with, if you are in a pediatric study, maybe there might be a study, an adult study. So you can apply the value, not directly, but you do some reduced by percentage and come up with some estimate. And then by varying the sample size, you have different confidence of what we're going to talk about today. So you can provide, with this number of patients, we have confidence interval of from what to what. So that kind of power calculation. It's not like comparing two tests, two groups. And if it's going to be a pilot study that has been done before, with a little bit of different direction, then you might have some idea how to do the power calculation. So some number, they want to see some number because you have to come up with some number. So we'll talk about it today. I'll add that. We have lots of slides today, so I'll try to rush. Variable is a characteristic that can vary in value among subjects in a sample or a population. And if you divide the type of variables into 2 different groups, one is categorical, one is quantitative. You know what's categorical variables, right? What are those? Can you come up with some example? Your own example? Yeah. Very good.
Colors?
Colors? Yeah. Categorical, there is no scale in there. And other type of variable is a quantitative variable. Can you come up with any quantitative variables?
pH,
age, right? Continuous. There's a scale. And within the categorical variable, there are 2 types: nominal scale and ordinal scale. Nominal scale, like gender, there is no scale within that group. But ordinal scale, there is some scale. It's not like continuous, but like low, medium, high, that kind of scale. None, mild, moderate, severe, that kind of some scale. From non to mild, mild to moderate, maybe the scale between those two might not be the same, right? Non to mild, maybe the scale different. If you can scale it, maybe the difference is like 3. But from mild to moderate, maybe the difference is like 10. So, but there is an order. And for quantitative variables, that's also called interval scale. So it has numerical intervals between each possible pair of values. In practice, ordinal categorical variables often treated as interval by assigning scores like grade or pain score. If it's A, B, C, D, E, then you can convert that into, that's the ordinal scale. You can convert that into 4, 3, 2, 1, 0 now, which is interval scale. Ordering of variable types from highest to lowest level of differentiation among levels are interval has the highest differentiation, and then ordinal and nominal.
What do you mean by differentiation?
So ordinal, there is a interval it's like height.
Any
You-
number between
Mhm. The scale can be really differentiable.
Oh, okay, I see.
So which means interval scale has, sometimes you collect the data as an interval variable, as a continuous, and then later on, for some interpretation, you might have to dichotomize a group into group A, B, C, low, medium, high. Then while you do that, interpretation might be easier, but you're losing some information. And sometimes when you run logistic regression or regression, the variable that's added as a continuous variable might be significantly associated with the outcome. But when you dichotomize it, it's possible that you might lose the significance and turn out to be not significantly associated with the outcome variable anymore, and people panic. Why? Because you are losing information. Another classification is by dividing whether it's discrete or continuous. Discrete variable, the possible values are a set of separate numbers, such as 0, 1, 2. Continuous is you can divide the values. It's an infinite continuum of possible values. We can collect data in a survey, in a study through a sample survey or through experiment. For example, in a survey study, you come up with a survey design and with a whole bunch of questions, and you ask, are you willing to treat patients with HIV/AIDS? Are you? Are you willing to treat patients with HIV/AIDS? With enough practice and knowledge and prevention methods, then yeah. So that kind of study is a survey design. And another design is an experimental design. And you design the study and you treat. The typical case is a randomized controlled trial of caries prevention in dental practice, this kind of study. Skip this one. So for example, in a survey study, though, the results depend greatly on the question wording. 2006, New York Times poll asked, do you favor a gasoline tax? Then 12% said yes. But when they changed the question as, do you favor a gasoline tax to reduce U.S. dependence on foreign oil? Then 55% said yes. And they further changed the question to, do you favor a gasoline tax to reduce global warming? And 59% yes.
So what type of bias is this?
What type of bias is this? I would say, if I have to name it, I would have to say questionnaire bias. So this shows that how important how important it is to how to design a study really change the results. So for some of the questionnaires are developed and they are registered and validated. So it's easier to use those because it's already validated. If you're going to design your study questionnaires, then you might have to justify it, and you might have to go through the validation process in the two different groups. So let's go over this. Number of movies seen this summer. The values that you can choose is 0, 1, 2, 3, 4. Is that quantitative or categorical? Is it nominal, ordinal, or interval scale? Nominal is there's no order within that. For number 1, number of movies seen this summer. Is it nominal, ordinal, interval scale? So nominal is like gender, female, male. There's no order at all. Ordinal is low, medium, high. Interval is, it has a scale with it. Interval, okay. Is it discrete? It's discrete, that's right. Favorite type?
Discrete meaning there's like a set.
Okay, that's 2.5.
It's not like 1.32, right? Favorite music type? That's categorical, nominal, and discrete. What about happiness? Quantitative. Right. Yeah, that's categorical, and it's ordinal, and is it continuous or discrete?
You can make it both ways.
Which one?
Like from happiness. Like you can say from scale of 0 to 10 how happy you are.
Oh yeah,
So
from
you can.
If that's like if you
We just
only
give them
3
option.
categories.
Okay.
If you
Then
give
it's
those.
going
That's
to be-
continuous because wouldn't that be kind of
Yeah, it's
different
continuous.
there's not like a set like you saw. Like, very happy can be different based on.
Oh, you-
like
if you are
like there's like a fluid to very happy because some people like it's not a defined like remember in movies like it's very defined. So wouldn't it be continuous?
So happiness, if you in your questionnaire you are asking the people to score from 0 to 10, and then they can pick any number in between, and then that's going to be continuous variable. So there's, let's say for example, there's a ruler line, and they can just put mark anywhere, so that's continuous. But you give them 3 choices, very happy. They have to pick among those 3 choices. Is it continuous?
You're saying it's discrete, but I don't understand how 0 to 10 is continuous because you have to pick 1, 2, 3. Like to me that seems discrete.
So if you put 0, 1, 2, 3, 4, and 10, that's discrete. But if you put a line,
Oh, and
no,
you just
that,
like kind of
right,
marks and it's like,
right,
okay.
that's continuous. So even you are using the same one line, depending on how you ask, it could be continuous variable or discrete variable. And this is discrete variable, ordinal and discrete. And order the variable types from highest to lowest level of differentiation among levels. So which one gives the highest level of differentiation? Ordinal, interval, or nominal? Interval. Next. Ordinal and nominal. Yeah. Okay, that's it for set 2 slides. Now we're going to talk about descriptive statistics. I have a very scratchy throat today, so I can't do it. So forgive me. Before you start any formal analyses, describing your data will give you an idea about your data, and it's also it's very very visually informative to see how your data looks like before you jump into any kind of analysis. And you can describe your data with tables and graphs. Um, and in order to make tables and graphs, the data has to be quantitative or categorical variables. And numerical description of center, variability, of position, that's used for quantitative variables. And for, oops. And you can also do the bivariate descriptions. I'm going to talk about that also. So tables, frequency tables, you have seen that a lot, right? It lists possible values of variable and number of times each occurs. For example, in a student survey about political ideology, 60 students were asked, and they were asked to mark from 1 to 7, 1 from very liberal to 7 very conservative. And then you got these results. 8 students said mark number 1, 24 students marked number 2, and when you graph that, that's a histogram that you come up with. So from that distribution, you know right away that most students answered number 2, and it's skewed. Is it skewed to the right or skewed to the left? Skewed to the skewed to the right. Skewed, like the tail is talking about the tail, the direction of the tail. So the tail is on the right, so it's skewed to the right. So it's very quick. Instead of reading these numbers, actually this graph shows right away about your data. This is another histogram, and it has lots of information. If you have categorical variables and also continuous variables combined, you can divide those 4 different groups of student status: dental, resident, and just the resident, and graduates, and resident graduates. So you have different histograms for each different group. Okay, and roughly when you look at the histograms, you can get the idea about the distribution. For example, the ideal data is bell-shaped, so the tails on each side are similar. And in this case, mean and median and mode are the same. Mean, you know what it is. What's the median?
The number.
Middle value. What's the mode? Oh yeah, very good. So those values are equal in that bell-shaped. We call normally distributed, a normal distribution. So that's the idea. And most of the statistic test assumes that your data, especially the outcome variable, is normally distributed. When it's skewed to the right, it has long right tail. And when you look at the mean and median, what does it look like? The mode is on the left, and the median, it's about in the middle, but the mean is far on the right-hand side. So you can tell that median is affected by what? Mean is affected by, yeah, mean, I'm sorry, mean is affected by
Mean is affected by the tail because there's outliers.
right. So the mean is most affected by the far right observation. So when the other case, skewed to the left. So again, the mean is affected by the smallest value, yes, by the tail value. And bimodal, there is also bimodal distribution. and that is, it seems like there are two normal distributions combined, and polarized opinions, you often see that kind of distribution. In this this kind of bimodal distributions, oftentimes you kind of dichotomize the results, and as yes/no, as a yes/no type binary variable. This is stem and leaf plot developed by John Tukey. This one gives all the information that you see from a histogram, but it also gives you the values, individual values, distribution and the individual values. And the stem is on the left-hand side, leaf is on the right-hand side. So the real values, so can you see the real values? What are the real values here?
Yeah, 36, 53, 57,
Yeah.
62, 63, 65,
Mhm.
72, 71, 73.
Right. Yeah. So those are the real values and the distribution at the same time. So this is really, really informative. And do you see any outlier?
Like 36.
Right.
And is it skewed to the what?
It's to the right. More on the.
Not imagine it on a.
It's more on the
more
right
on
side,
the right,
it's
to
left.
the left.
Yeah, it's skewed to the left.
Yeah.
That's right.
Picture,
Yeah,
it's
just picture like this.
Mhm.
You were sitting from this side. Right. Okay, because skewed to the. So sometimes people start from the bottom to the top. Then, in that case, that's skewed to the right. This person start from the top to the bottom for the bigger value. For the numerical descriptions, we normally denote a y observation variable y, and its observation as y1, y2 to yn, which is you have n observations. And for median, it's easy. It's a middle value. Mean, it's a summation of each individual observation divided by the sample size. And something's missing here. Summation mark is missing here. So there's summation mark here.
Yes, sigma.
Yeah, sigma. That's a median. It's easy. So, for example, annual per capita carbon dioxide emissions. I don't know why this is cut off like this. Let's see. Metric tons. They collected data on 8 largest nations in population size. So the values they collected was 0.3 for Bangladesh, 1.8 for Brazil, 2.3 for China, 1.2 for India, Indonesia 1.4, Pakistan 1.7, Russia 9.9, US 20.1. Wow, huge number. So in calculating those, these are the ordered sample values, 0.3 to 20.1. Just looking at those values, what do you see? What stands out to you? Oh yeah, outlier. The minimum 0.3, maximum 20.1. So by just ordering the values, you have an idea. Wow, there's one huge outlier. So for a median, you just ordered. So from left-hand side, you have 1, 2, 3. From right-hand side, you have 1, 2, 3. So you have 2 middle values. Then what do you do?
Okay.
Get the average. Then that's a median. And the mean value is 4.7. So when you look at median and mean value, are they same?
No, because of the outlier.
Right. So since this is skewed to the right, mean is much bigger than median. So when you read your articles, when you review the articles, then on the table 1, they normally report median, range, and mean. So just by looking at those median and
Can we
mean,
not consider the outlier or somehow statistically like manipulate them so that don't be part of our data.
Oh, so what do you do with the outliers?
Yeah.
So
I think there should be another statistical analysis on that.
non-parametric test, right? So as you can see, the mean is so much affected by the one observation, so it's kind of misleading. So what you can do is, in that case, instead of doing t-test, which is like comparing the mean, you can do the rank test. You can rank 1, 2, 3, 4, 5, 6, 7, 8, and then you sum the rank. And so in this case, reporting the median is more appropriate. And when you're comparing like two groups, then you kind of sum the rank and then compare. In that way, you are not affected by you kind of scaling them equally. You just take the order and compare whether there's a difference between those two. And comparing two means, like two ranks, and the ranks in the two groups is Wilcoxon rank sum test. Have you heard of it?
I heard it before.
Mann-Whitney test. Have you heard of it? Signed rank test, Wilcoxon rank sum test, Mann-Whitney test. Wilcoxon, yeah, that's a
They're all
non-parametric.
non-parametric.
They're
That
non.
one went
So they're all non-parametric. Yeah. And sometimes in that case, if the outlier is really, really severe, and you have a whole bunch of group with outlying in this end, a whole bunch of group outlying in this end, then you might want to cut into low, medium, high, and then do like logistic regression, ordinal logistic regression, or there are so many options after that. And so when you review article, mean and median, it can give you some ideas about the distributions. If they are not very close together, then the distribution is not normal. And when you're asked to review article as a reviewer, then you can point on that. Did you do non-parametric test? Did you still compare mean? So, example, New York Yankees baseball team 2006, mean salary was $7 million. Median, is it close to statistician? I know, dentist. Median salary is 2.9 million. So mean and median, they are quite different, right? What's the direction of skewness? The mean is much bigger than median.
Is it to the right?
Right, skewed to the right. Because it's affected by the big values. Can you give an example that you would expect the mean is much smaller than the median?
Reverse the mean and median.
Smart. Okay. What about other case? Mean is much smaller than the median. So the shape of the distribution is, it's whole bunch, so it's like this. Yeah. Whole bunch is on the upper side, but very few, very low values.
Is it like children's birth weight?
Birth weight. GPA, the GRE score, they say. Academic scores. The whole bunch on top. Of course, not everybody on top, but very, very few in the very low scores.
But shouldn't all the standardized tests like follow the bell curve or no?
They don't.
They don't?
No. I'm doing a project right now, reading ability and math. They don't. It's not bell curve. Now we talked about the center of the distribution, like median, mean, mode. Now we can describe the data with variability, how variable they are. The first one we can use is range. So you can talk about, you measured blood pressure and the range is huge. So the first impression that you get from there is, wow, there are so many outliers, very low value and very high value. So that's the impression that you get. And standard deviation is a typical distance from the mean. So if the range is big, then standard deviation will be big too. What's the range?
Distance between highest and lowest numbers.
Mm-hmm. And the variance is, oh, where are all my minus signs there? Okay, it's missing. So for variance, you subtract the average value from each observation and you sum up. Where did all the sum? Sigma. All my sigma is gone. Oh, maybe because this is Mac.
Compatible, maybe.
Mac. Because I used
Yeah.
maybe that's a problem. Yeah. So here there should be a sigma sign here. So you sum up the difference for each observation, the difference from the average, and you square them, and then you sum it up, and then you divide by n minus 1, and that's a variance.
I remember sometimes it was n, not n minus 1. Am I right? When do we minus 1? When do we...
So n minus 1 is for the sample variance. N is for the population variance. But do we know population variance? We don't, right? So in real life, we use, most of the time, we do n minus 1.
Okay. So what does this minus 1 comes from? That we don't have in population, but we have it in first sample.
So there is a way to estimate the bias.
Okay.
And if you use n for the sample, there's a bias. So if we divide by n minus 1, then there's no bias. That's how we came up with n minus 1. And you get the square root of the variance. That's a standard deviation. So you took some stat class before, right?
Like me 10 years ago. Wait.
I took that under, I have to remember
Not 10 years ago. Like 6 or 7 years ago. Yeah, 6 or 7 years
So
ago.
you learn all the probabilities and some regressions, right? ANOVAs. And,
Really?
You know that.
uh-huh.
I took
Within
a graduate course like Biostat. That's how I
mine wasn't
remember.
graduate, mine was undergrad.
We took all the classes. So yeah, this will refresh it. You'll remember this.
But you know, when you don't
This
use
stuff I
it, then
remember.
it all goes
I
from
remember
your
this
mind.
stuff, but I don't remember like the ins and outs of like t-tests and yoga. I just don't remember it. But
Yeah.
I know that right now I only remember that these are the tests for hypothesis testing. That's all I remember. But
Yeah. It will kind of bring it, because you can conceptualize through this course, because we'll be until estimation and significance test I'm going to cover, and then Dr. Tseng will come and do the review on the comparisons. So for this, so 9 children were asked who come to a dental clinic. Do you mind reading those? Sorry. Yeah, observations. And the average is 5.0.
which one would the average
Mm-hmm.
divided by 1 minus 1?
Right. And the variance is,
Square root
so S is what?
1.7.
Mm-hmm. That's standard deviation.
That means like, oh, that's standard deviation, so it's yeah.
Right.
That's 68%.
Very good memory, actually. Mm-hmm. Yeah. We'll
But
go over that.
If it's bell shaped, if it's not bell
That's
shaped, then we
yes,
cannot.
that's bullshit.
That's
if
right.
it's not bell shaped, then we cannot.
Right.
Come on, let's make a comment. Keep to the bells.
So when you look at the mean 5.0, and then when you look at the data, the minimum is 2, maximum is 7. So is it kind of bell-shaped? it looks like. Not too bad, right? You don't have like 20 or 30 over there. Okay. So properties of the standard deviation, it's always positive. It's equal only if all the observations are equal. Then you don't even have to talk about that. It's
and it's
so
going
easy.
to be the only time that variance can be equal to standard deviation if it's equal to 1 as well. Yes. When can variance be equal to standard deviation?
When the sample size is 2.
Yes. 2 minus 1 and then.
Uh-huh.
You guys see these things?
Okay, don't worry.
Yeah, or
Don't worry.
over
No.
When it's 1, right?
Yeah.
And the variance is 1. Okay. And standard deviation increases with the amount of variation around the mean. And let's look at the distribution. So as you said, this is a standard normal distribution. And if its distribution is approximately bell-shaped, 68% of the data is within the 1 standard deviation of mean. And 95% of the data lies within 2 standard deviation of the mean. And about 99% of the data lies within the 3 standard deviation of the mean. And when we do the t-test or f-test or anything, we assume they have distribution, right? So when we do the t-test or regression, and then you get the p-value, it's all coming from this kind of distribution. So if your data is not normally distributed, maybe what you're doing and what your results, assuming normal distribution, might not be valid. So for example, if you have binary data, the outcome variable is yes, no, or disease, no disease, symptom, no symptom, then can you assume it's normal? You cannot, because it's not normal, right? You have 2 values. And so in that case, you do something called logistic regression, right? Or if it's univariable analysis, you compare the mean of those, for example, with those who had symptoms and not symptoms, you compare the age, average mean of those. So there are many, many different ways of doing it, but if it's a multivariable analysis, you do logistic regression. Yes and no is an outcome variable. And there is no assumptions, underlying assumptions as normal distribution. We'll talk about that later more. Again, example, they asked General Society survey. They asked number of close friends you have, and the mean was 7.4 with a standard deviation of 11. It's quite widely distributed, 11.0. Is it skewed to right or left if the median is 5? Skewed to the right. Skewed to the right.
But not that much, is it? Because
Not that much. But when you think about, now look at the standard deviation is 11.0.
Oh, yeah. Then.
But you can't have negative friends, right? So 0 is the minimum number. Maybe if you have enemies. So standard deviation is 11. So you can imagine, oh, so data only can go from 0 and up, right? But standard deviation is 11. So it's really, really skewed to the right. You can have a guess, right? Selling price of a home in Syracuse, New York. If mean is $130,000, this is really non-realistic, but for example, if the mean is $130,000, what would be the realistic standard deviation? Trying to give you some idea about these numbers.
Maybe.
Is 0?
No.
No.
Say 1,000.
No. It's going to be 50K.
Oh yeah, the 69. Yeah.
Mm-hmm. Yeah. So 50K. Everybody agree? 1 million is it's really non-realistic. 1,000 is not realistic either. That means almost all the houses are
Yeah.
right. And S equals 0 means every
All the
single
sides.
house, right? Every single house is $130,000. Okay. Measure of position. Now we are talking about the percentage. We talked about the continuous variable. Now, yeah, we are still talking about the continuous variable, but we can also talk about the measure of position, pth percentile. So we often talk about 25th percentile, median, 75th percentile. And the difference between 75th and 25th, that's interquartile range, we call IQR. And that gives you a idea about the distribution. So this one also, the guy who came up with stem and lift, the plot, he also came up with box whisper plot. I think he really liked graphs.
I like to
Yeah. So what does it tell? Can you, from this plot? 3 outliers.
The 50%, that's the middle, and then it does like a little switch up, that's 25 to.
To right.
This one is skewed to right.
Yes.
Right. So this gives almost all the information, right? So it tells you the outliers, minimum, maximum, median. So where would be the mean, do you think?
Upper and upper two.
Right. Somewhere above the median line, right? So in here, the maximum is not really the maximum that you see on the graph, right? They put minimum and maximum, and then there are 3 outliers that falls outside the maximum. Why is that? How do they decide the outliers?
It's very different than the other. I don't know.
So there is a rule in this graph. So when you go to the low right-hand side, if low quartile is 2, upper quartile is 10, the interquartile range is 8, then the outlier above is 10, which is the upper quartile, plus 1.5 times interquartile range, which is 22. So any points that's lying above 22, those are considered outliers.
So why do you consider 20 as that?
20.
It's 30, 47, 39, maybe it's another.
That must be.
A
I don't
typo?
think. I think that's a observation value, not the value itself. The value is on the
Even the
y-axis.
value is above the 20, but I can see
Yeah.
the dot on 20.
So I think that's the observation identifier, identifying number. So do you see the star? These others are circle, but the others are star. This is really, really extreme outlier. You can also express that in a bivariate description. So if you have continuous variable and a categorical variable, or you want to express those in one plot, or if you want to show the association between 2 or more variables, for example, how does number of dental caries depend on gender, income, education, age, working status, or other factors? In this case, response variable is the outcome variable. Explanatory variable is are usually the groups to compare. So let's look at this graph. So you can, through this graph, you can summarize the association. Categorical variables is the data show data using contingency tables. Quantitative variables we can show using scatter plots. And if you have a mixture of categorical variable and quantitative variable, you can use side-by-side box plot for the groups. So from here, what can you see? What can you see from this graph? So overall, male and female, what do you see? Yeah, male and female, they are kind of, when you go to the minimum and maximum, they're pretty similar, right? Male and female. But what about the length of that blue color and the green color in male and female? It's male has wide ranges, right? Wider range, and female has smaller. So the variation is smaller in the female. And what about between those two groups by carries? Is there any difference? So when you look at the green by green in male and green in female, do you think you will get any statistical difference when you compare those two groups? No, right? They kind of overlap, right? What about the blue versus blue? I don't think so. Yeah, I don't think you will get any difference between those two. Okay. This is another side-by-side box whisker plot. The reason they call whisker is the box and this line. These are called whiskers. And this is income by highest degree. So what do you see from this graph?
The higher the education, the more skewed it's going to be.
Right. And
But overall, I don't see any statistical difference.
right. So when you look at the median, it's kind of linear trend of going up, right? Linear, a little bit higher, and the higher groups. But
is it statistically significant?
I think.
Because it's hard to tell actually.
Right, and also depends on the sample size. And seems like if the sample size is big enough, let's assume their sample sizes are big enough, I think you will be able to see the difference between some college and bachelor. I think you will be able to see some difference. Bachelor, the median is like close to the lower quartile of bachelors, right? And bachelor and higher degree, I think you will also be able to see some difference. It really depends on the sample size. So when some of the people just have some college, they're doing, some people better than majority of higher degrees. Now this is a contingency table. They asked about happiness and family income. This is GSS 2008 data. And you can make this kind of table, income by happiness table, and you put the numbers who fall into each cell, And from this cell, what can you say about this table, about these values? Where do you see most numbers? From first row, above average. Income is above average. Where do the majority of people fall? Pretty happy. What about average income? Right.
So happiness doesn't relate to income.
It seems like when you just look at those numbers, right? It doesn't seem like it's, but let's look at the above average, not too happy, 26 people, right? The fewest sample size in that row. What about below average?
But the thing is that total out, they had 423, and then like the other one has 800, and then the other one has around 700. So just by looking at numbers, let's say 26 over there and 170 over there. Should be difference.
So, right. So the percentage.
Yeah, we
so-
should go with.
So when you go to the right-hand side, 39% of above average income, they were very happy. Those who had average income, 33% were very happy. But below average, 90% were very happy. So it seems like as long as you have about average or above average, you are very happy, unless you don't. It's not below average. So this is a percentage. So now what do you see? What can you conclude about the corresponding population?
So there is a kind of relation between income and not being happy.
Do you see difference between above average income or average income with those two groups? They're kind of
6% versus 13%.
not too much difference, right? But what about below average?
Really.
Yeah. But to be pretty happy, it seems like majority of them, more than half of them are pretty happy, right?
Overall, you can be happy with low income.
That's right. Good conclusion. Now this is a scatter plot. You have seen this a lot, I'm pretty sure. And UN data for several nations on fertility versus per capita gross domestic product GDP. What do you see from there? Is it positive relationship? Or is it negative relationship, would you say? It's more of negative, right? And above certain GDP dollars, does it change? Fertility rate, it's flattened, right? So so before you start any analysis, it's really important to visually see what kind of data you have. So can you assume it's a linear relationship between those two? Fertility and GDP dollars?
At certain GDP, yes, but overall, no.
Right. So it's not, it would be more a curve, right? Or piecewise regression. So if you're going to do the regression, I would do piecewise. So between 20,000 and 30,000, I would, before about 25,000, I would do negative linear relationship. And then after that, maybe flat. So it will be a two piecewise regression or a curve. So if you haven't seen the graph, you might have just fit the data, assuming it's linear, and you might get the significant results, but it might not be a correct estimate. This is another survey in Florida. It's studying about the mental health and life events. So from this graph, what do you see from this data? Is there any relationship between mental health and life events? Right. And possible positive, right?
Yes.
But why do you say it's possible positive?
Because you can really see it going up, but since it's not like tight to one line, it's weak. So,
Uh-huh.
but you can still see.
Mm-hmm. Is your relationship affected by those two outliers on top?
No, I still think it looks really
Yeah, without those two plots, do you think it's two dots? Do you think they're still linear? Maybe weaker, right?
Yeah,
So it's really, again, I'm just showing this example to show you that how important it is to visually examine your data. Because those two data might be outliers or valid outliers, or it could be a mistake, data entry error, recording error. So it's worth checking again for those outlier values because your relationship could change depending on that. This is the Massachusetts Lottery data for 37 communities. What does this tell? Curved, right? And negative. So again, this shows it has the instant feeling about what kind of data you have, what kind of results you can expect. Now, you often hear about correlation between two variables, right? Correlation coefficients. And do you know the range of possible correlation coefficients? So if it's positive, what kind of values do you get as a correlation coefficient? 3.5? Yeah, 0 to 1. If it's negative correlation, it's negative 1 to 0. So let's see. Let's look at the values here. So if there is 0 correlation, the graph looks like up there, left top. There is no correlation. If it's negative 0.3 correlation, it's on the right, top row. Middle row, correlation 0.5. And let's see, the bottom row, right. If negative 0.99 correlation, the data looks like that. If it's negative 1, how does it look? How would that look like? One straight line, right? Mm-hmm. Yeah. So that's a correlation. And can you look at the correlation for categorical variables? Right. Mm-hmm. That's right. This is for continuous variables.
it was so bad.
In making statistical inference, there are two methods. There are many methods, but basically we start with estimation and significance testing. Estimation, so when we estimate population parameters, we can never use population, so we need to sample from population, right? So when we get sample statistics, we are estimating a parameter values of the population through the sample. And when we talk about 95 confidence interval, when we get mean of 1.5, the slides in this computer, in this laptop, wiped off all my formulas and everything I went through. They look horrible, but I'll try to fill in. So the mean is 1.5, standard deviation of 2.2, and the value. So when we get confidence interval, we say 95% confident that the population mean stay between 1.4 and 1.6. Significance testing, and we do significance testing to have an idea of the effect of a certain drug or treatment, or to assess the association. Article in Science 2008, quoted from there, we hypothesize that spending money on other people have a more positive impact on happiness than spending money on oneself. So that was their hypothesis. So once you build a hypothesis, you can come up with a significance testing. Do you agree? What do you think about this hypothesis?
Yeah.
Do you think the results will be, you will have positive results or negative results? Positive.
Listen, please.
Huh?
Listen. Some of your friends.
Oh, I did not go to some really
I'm
high.
joking.
She
I
epitome
know.
of that hypothesis.
Okay. So in making statistical inference, the goal is to use sample data to estimate values of population parameter. So you can have point estimate or interval estimate. Point estimate is a single statistic value that is the best guess for the parameter value. Interval estimate, one typical example is a confidence interval. So sample mean estimate of population is average, but that's a sample average. So whenever there is an estimate, there's a hat, cap or hat. So that means that's an estimate. And when there's no hat, that's a parameter. And standard deviation, sample standard deviation, estimate population standard deviation, and sample proportion, P, pi hat, you usually call pi hat estimates population proportion pi. This inserted this car instead of pi. It's a pi. Proportion. So confidence interval is an interval of numbers believed to contain the parameter value. And the confidence interval have the form point estimate plus minus margin of error. So usually mean plus minus something, standard deviation times something. And confidence interval for proportion is also in the same format, p hat plus minus that usually 1.96 times the standard error. And I think we better skip this. It replaced with blanks and everything. But one thing is standard deviation of a proportion is square root of pi times 1 minus pi. So with probability 0.95, the sample proportion pi hat falls within 1.96 standard error of population proportion pi. Also, it looks consistently. So the confidence interval, you will have to go to the slides that I sent to Hamida. She uploaded to somewhere that you have access, right?
We
It
have
has
also
slides.
Mac all of us. So
Oh, you do?
maybe she can like change it to PDF and then send the PDF to
Oh,
us.
I see.
And
Okay. All right. Yeah, you might want to remind her. So, so the format of confidence interval is the estimate. It could be mean, or it could be proportion plus minus 1.96 times standard error. The 1.996 is coming from where? It's coming from the value here. 1.96 is, if you see my error right here, right here. So it's 1.96. That's showing that 2.5% is above that value, and 2.5% of the data is below 1.96 here. It's right here. Do you see it? Do you see the error? Right over here. So that's the value that's coming from 1.96 is coming from there. So it's showing that 95% of the data stays within that range, minus 1.96 to plus 1.96. So confidence interval is the interpretation of confidence interval is that you are 95% confident that the true value lies within that range. Okay. Oh, so it's talking about the same thing. And so what percentage of 18 to 22-year-old Americans report being very happy? GSS data, General Society survey data. 35 of 164 says they are very happy. So 35 out of 164 is 0.213. So that's the estimate, right? And the standard error of that percentage is 0.213, which is the p times 1 minus p. So it's 0.787 divided by the total sample size, 164. So the standard error of that percentage is 0.032. So the confidence interval for that estimate is 0.15 to 0.28. So the interpretation is we are 95% confident that the population proportion who are very happy is between 0.15 and 0.28.
So if the mean lies between these range, then means that, what does that mean?
So this is the proportion, confidence interval of that proportion, right? So it should be between those two values. Confusing?
But like for this study, this is not a continuous, like very happy, and then not too happy. So it's not. It's not. It's kind of like a. Can we use it for? This is not quantitative data. Am I right?
This is not quantitative, but this is an estimate of the percentage. The 31% said they're very happy, right?
Okay.
And we're talking about the certainty about that percentage.
Oh, I see.
Certainty. How certain are you? Is this a real percentage that we can talk about?
Okay.
So how much certainty is there in that value? And the confidence interval says 0.15 to 0.28. Okay. So we are 95% confident that 18 to 22-year-old people, Americans, feel very happy, and the value is between 0.15 and 0.28. You just mentioned include 0. Did you say that?
No.
No? Okay. That comes later when you do the test. When you do the test, and if the confidence interval includes 0 or confidence interval include 1, what does it mean? That comes in the analysis later on. And sometimes you might want to say, what about 99% confidence interval? You sometimes hear about it. If you want to have 99% confidence, do you think the confidence interval will be wider or smaller, narrower? To have more confidence,
the range is going to be smaller.
Really think about it. If you want to have
The two numbers are going to be closer together.
Okay, so let's, for example,
Like for example, it should be between like 0.2 to 0.3. No, actually, this is for if it's. What was the confidence interval for 95%?
95% confidence was 0.15 to 0.28. But this is wider, right? Why? Let's say, for example, your height. Your height is, how tall are you?
5'11".
5'11". So, okay, I'm 95% confident without hearing it. I'm 95% confident you're between 5 and 6. But let's say.
I see what you're saying, yeah.
Mm-hmm. I'm 99% confident you're between 4 and 10.
Yes.
Or almost 100% confident you're between 4 and 10. Is wider,
Yes,
but I'm
indeed.
much more confident because are you 100%
So the higher
confident?
confidence interval is not good, basically.
It's not good. Yeah, it's
Yeah,
uncertainty, more
yes.
uncertainty. Are you 100% confident that he's between 1 and 10?
I'm higher. Is a higher confidence level always wider? Or
Always
you said it,
wider.
it is or it is?
Because you increase the chances, you decrease.
No, yeah,
you
I
want to
understand.
decrease the chances of error, so you make it wider.
Yeah.
Because
I didn't know if there was a way to like limit.
how confident are you that I'm between 5 pounds and 1,000 pounds?
100.
100%, right?
Yeah.
Because it's so wide. But if I narrow it down, your confidence reduces.
No, I understand.
Right?
I understand
Mm-hmm.
the concept. I
Mhm.
was just wondering if there was a way to like have a higher confidence interval without having to increase. Like if you could, I don't know if you increase your participants or if you like if that would like
So if your confidence interval, not the percentage, but the interval is narrow, that means you have
less.
the standard error goes down.
Standard error.
Mhm.
Okay.
Then you have high confidence. You're pretty sure its value is very close to that. So let's, for example, you're 95% confidence, and the interval is 1 to 3. You're 95% confidence, but your range, the interval is 1 to 10. Which data is more reliable? Smaller interval, right? So you were talking about two different concepts.
Oh, okay.
Mhm.
That's talking about a little bit.
Yes. Yeah. So suppose sample proportion of 0.213 was based on sample size of 656 instead of 164. So you increase the sample size, then the standard error is reduced, right? Instead of 0.032 to 0.016, then your confidence interval will be shorter. So greater sample size, right? So greater sample size gives narrower confidence interval, but you're still 95% confident that's in the interval. So you want to reduce the interval with a 95% confidence. So if you want to halve the width of the confidence interval, then how many times do you increase the sample size? If you want to make it half. Answer is right there.
Ask the question if you want to make the confidence interval
Half, reduced by half. Instead of 2 to 4, you want to make it 2 to 3. That's half, right? Confidence interval was 2, but now you want it to make it to 1. Instead of 2 to 4, you want to make it 2 to 3. then how many sample size, how much more sample size do you need to collect? Quadruple. Do you know why?
Square root.
Yes, square root of n, because of that. So you asked about the sample size calculation. So the sample size, if you want, for the pilot study, you normally present the sample size needed for the confidence interval, 95 confidence interval. I think with 95% confidence, range will be this and this. But sometimes if you present very wide interval, then the reviewer might say, no, this is not informative. You need to reduce your.
So do we still use the same power calculation formula for like pilot studies?
Yeah. So if you want to reduce to half, then you have to quadruple there, which is significant, very, very significant. Because when the feasibility is like if you can collect about 20 patients, this type of patients, maybe 20 patients per year, and they are asking you to quadruple, it's not feasible at all. You have to do the long-term study, or you have to collaborate with other centers. So it has a lot of impact. And the mean is the same. As long as you get the mean estimate and the standard error, then you can get the confidence interval. Calculation. Sometimes you talk about normal distribution and t-distribution, right? And sample is normally we use t-distribution. And when you look at the distribution, normal is the shape with a very high peak. That's a standard normal distribution. When you compare it to the t-distribution, it has heavier tail. The peak is lower than standard normal. But do you know when t-distribution becomes very close to normal distribution? Sometimes you cannot assume normal distribution, but sometimes it's okay to assume normal distribution. The distribution becomes close to each other when the sample size is bigger than 30. So you might encounter statisticians saying, you bring your data to statisticians.
So if you wanted to use t-test, you should always have more than 30 participants.
That's good. Yeah, that's very good. At least you will have some valid results.
So 30 in each group, or like 30?
30 in each group is good.
Okay.
Yeah.
What if we have groups inside our groups? For example, like disease-free, but like we have a group that has like this type of disease, this group we don't have this type of disease, but in the group that has this type of disease.
Subdivisions.
Yes.
And then later on, when you use all the subdivisions, you have like 2 to 3 patients in each subdivided
Exactly.
group.
So can we still use t-test or no?
So when you have like variable A, variable B, variable C, and within variable A you have
Exactly.
B. In that case, you can compare variable A between those two groups, variable B between those two groups univariably.
Okay.
And they say for the multivariable analysis, each time you add one more variable, you need to have 20 to 30 additional observations. That's coming from there. But
that's not always going to happen like that.
That's not going to happen, especially in the lab setting.
Exactly.
And we still
like if you want to do like pilot studies or whatever,
right.
That's...
Yeah, we still try.
So like, for example, you have to recruit, if you have like 2 categories and then 2 in each one, so it's going to be 8 and 8 times 30, so like 300 people we have to recruit. That's
yeah, it's not possible. So people usually with a smaller sample size come to us. It's analysis will be very simple. We only have few sample size. It's totally the opposite case.
Yes.
Small the sample size, we spend much more time trying to
Address
generate the
it.
valid, address the question, trying to generate the valid question, because we have to try so hard not to violate any statistical assumptions, but still want to generate some results. If you have bigger sample size, they feel bad saying, oh, this is going to take long. Actually, it's much easier for statisticians to generate. So you still try to test, because that's what you have. There is no other way you can get, but you need to be very careful. You need to talk to statisticians, and every approach you really need to be cautious. Still, some valid results can come out, but big conclusion cannot be made from those sample sizes, but some implication for the bigger study can be drawn from there. And this is a part of T-table. So,
Where's the camera?
oh, there's the camera again.
And
Okay.
-1.
Okay, so I think it's trying to say,
And -1. Yeah.
30?
Just below. What's that?
yeah, maybe 30, I don't know, 30? Yeah. So if the degree of freedom is infinity, of course, it's a standard normal distribution. Yeah, I think it's infinity. The infinity,
Eight.
yeah, so if you look at this 1.96, that's the value that you get for the standard normal distribution, right? So if the sample size is infinity, it's we can assume it's normal. And population mean, I already did that. So there's an example, anorexia study. Weight was measured before and after a period of treatment, and Y is the weight at end minus weight at beginning. And 17 girls received family therapy, and the weight change data was collected like that for 17 girls. So that's the value that you get. And when you make a frequency table, this is how it looks like. So what does it tell from this graph? So one girl lost how much? So one girl, so this one is weight at end minus weight at beginning. So if it's positive, that means the end minus beginning. So if it's positive, that means they gain weight. So if it's big minus, that means gained a lot. Already? Yeah, so, and big positive means they big negative means
they lost a lot, and then because
right.
it was they gained a lot.
Mm-hmm. Yeah. So this shows you how the data looks like. And anybody use SPSS here? Or Stata? Or R or SAS? This one is T distribution. The T table, T distribution table. So whenever you do the hand calculation, you use this table. But actually, when you use software, the value is generated for you, confidence interval is generated for you, but they are using this table distribution. So you can do, using, for example, if you use SPSS, you just click on the Analyze, Compare Means, One Sample T-Test. Why is it One Sample T-Test? It's before and after, right? Two sample t-test is for the two independent groups. One sample t-test is there are only 17 girls. They are the one group, right? It's just before and after. So you subtract the weight ending weight minus initial weight. So it's one sample t-test, but you're testing whether the change is equal to 0. And then it will spit out the p-values. When they generate the p-values, they're using this t-table example. And GSS, the survey asked, on average day, how many hours do you personally watch TV? They asked 899 people. The average was 2.865, standard deviation was 2.617. And what's the degree of freedom we are going to be using? When you use t-distribution, there's always degree of freedom they ask about. And degree of freedom is n-1, observation minus 1, so it's 898. It's very huge. So from there, you know that t-distribution is very close to z-distribution, which is standard normal. So the value that you're going to be using is 1.96. 1.96 coming from, it erased here. Here, t, this will be 1.96 times standard error. Okay, this is a multiple choice question. Your confidence interval is 2.865 plus minus 0.171, or the confidence interval is 2.69 to 3.04. How do you interpret this? Which one is the correct answer? What's very similar to A? Which answer is A and C? When you calculate, so all the values that over there is from sample, right? 2.69 and 3.04 is from the sample. But the reason that you're doing that is, so C. The answer is C. So you're 95% confident the population mean is between 2.69 and 3.04. So you have some inference about the population. The reason you're using the sample? Right. Yes. Yes. Sample is right there, right? Yeah. But we are talking about this inference about the population. Time is significance test. Maybe I'll have to ask Dr. Sang to cover this part. This whole topic. I'll ask Dr. Sang to cover this. Because he will be covering the test anyway, so that can be easily merged into his talk. Any questions?
So for next time, we need an idea
And the hypothesis.
and what we want to test. And then the next time it would be more.
The fifth, yeah.
So this
Crystal.
focus on like what our idea is and what our hypothesis is. Research question.
Do you have a mentor who could give you some ideas?
Yeah.
And since you, Okay, good. Mhm. Mm, mm, okay. Good.